I wanted to show a little something that I stumbled on. And this may be documented, likely is, but sometimes we have a way of looking so into the weeds that when we pull our heads up, we find that something's, mentioned here, mentioned there. Nonetheless, when we poke our head into the weeds, we can often find tools that are useful for us. We're talking about the development, at least of a quantum computer. And we'd like this computer to, and this is the sole focus of this video here, is we'd like this computer to work with polynomial equations, literally solve polynomials of higher than degree order 2, higher than quadratics. We'd like it to solve polynomial equations. Uh, but as we know, classical computing, there are a lot of steps in order to solve higher order polynomials. So that's the motivation. So let's look at some properties. And we're looking at x because we're looking at x and we're going to look at polynomials of x, like x squared, 2x squared, x squared, So let's go ahead and get started. Let's look at the line x, right? X is just a line with some slope of 1, slope of 1. And let's look at sine of x. Okay, notice the similarity there, right? And if you do remember from grade school, there's the small angle approximation. Don't know if you remember, encountering that back in grade school, right? So for certain small angles, now look at how close we're zoomed in here, right? The range, the domain here, we're going from about negative 0.6 to a positive 0.6, like very narrow window, if you will. And we're also going up and down like 0.4, so not even 1. But let's keep going, right? We have x, and then we have sine of x. Now, the reason I chose sine of x and am looking into this is we're looking to accelerate polynomial equations. So in order to do that, we're using a quantum computer. A quantum computer is a computer based off waves. So we need somehow to marry the two ideas. We need a wave computer that goes fast on waves to be able to perform polynomial equations. And we're going to do that by looking at these approximations. So we have x and we have sine of x. Now, if you notice, there is a little divergence, right? As you diverge away from a certain fixed bound, you'll notice that sine of x, they diverge, right? There's a little bit of divergence there, but we're really focused around this 0 anyway. We're focused on the root of the equation. Like most of the time, we'll be focused on this root. So let's look at 2x. Notice that it's that, if you're familiar with equations, y equals x is just y equals 2x is just it's a line like x was, but it has a higher slope of 2. Then we have, we can look at sine of 2x. Notice the similarity there. Wow, they're almost identical. So, right, here's the wave equation form, and then here's the polynomial form. Okay, again, we have sine 2x squared, right? This is just I just used Desmos, it got creative here, but we have sine of 2x times sine of 2x. That's sine of 2x squared, right? So we have that form. That's a quadratic form, right? And now look at the polynomial version. Boom. Like almost identical, right? So let's keep going, higher orders, right? So we have, let's look at x squared. X squared is another type of quadratic degree, or degree 2 polynomial, and it has this type of trend. We're just looking at trends right now. Sine squared of x, right? Similar trend. How about sine cubed of x, right? Sine cubed, that's the wave equation form, and here's the polynomial form. Wave equation form, polynomial form. Okay, you see a pattern here? Sine, let's start with x to the 4th power, right? Let's look at sine of x to the 4th power. There's that trend again, almost identical, just a little bit of again, they diverge just ever so slightly, okay? If we were to distinguish them, Notice that the sign is a little bit lower, but they have the same trend. And also at 0, they're as you approach the 0, they're identical, or they approach identical. However you math experts want to say it. There's a limit, infinite limit. Okay, so let's go. I think one more degree 5, order 5. So we have x to the 5th power, and then we have sine of x to the 5th power. Again, similar trend. If I didn't show you them relative to one another, you would almost not know the difference. So this is one of the areas that we're going to use wave dynamics in order to accelerate polynomial equations. I don't have it all figured out yet. I don't know, but there's a strong link here, and this idea, this is a strong idea in one of the areas that I think we're going to see a lot of accelerations. We're going to see wave equations. You know, when you're zoomed in to a certain degree, they're going to approximate polynomials, and we'll use that property in order to, solve really high order polynomials. Yeah, so just was excited about that. Wanted to share. These are always unscripted videos, but yeah, and they're mostly to just record stuff. I enjoy doing them. But if you're listening and you appreciate this too, awesome. Welcome. Thank you.